So in today's class, we will discuss about magnetic flux in a toroid. Toroid is a circular shaped core to which there are, as you can see here, there are number of turns wound to the copper wires wound on the this circular coil. So this can be shown as you can see here. You can also represent it like this. Okay, turns, number of turns are wound on this coil. There is one exit and there is one entry. The radius of this toroid is r. The radius of this toroid is r, and the number of the flux lines phi are passing through the coil. There are, when there is a magnetic field lines are induced in the coil, there will be some field lines which are in the air. These are known as leakage flux. Some flux lines in the air, these are generally referred as leakage flux. As the permeability of iron is higher than that of the air, permeability of the iron is very much higher than that of the air. The flux in the magnetic material is large. Flux in the iron is very large when compared to that of the leakage flux. Okay, so when the coil carries a current I, the coil will carry a current I. Magnetic lines of forces will be confined within the core, because, as I told, the permeability of the iron is more than that of the permeability of the air. Therefore, the flux lines inside the magnetic material will be more than flux lines in the free space or air. Okay, so we can write it as the flux lines F. The flux lines F can be written as F is equal to N into I ampere turns. N into I ampere turns. So the magnetic field intensity H, the magnetic field intensity H can be written as Ni divided by 2 pi r, where 2 pi r is the circumference, 2 pi r is the circumference of the toroid. 2 pi is the circumference of the toroid. R is A plus B, where B is the outer diameter, and A is the inner one. A is the inner one. So R is A plus B. We are basically considering the middle of the toroid as the radius. Okay. The flux intensity, the average flux intensity in the toroid can be written as mu naught mu r into H. Therefore, it can be written as B is equal to mu naught mu r into N into I divided by 2 pi r. Mu naught mu r is equal to N into I divided by 2 pi r. So the what is B? B is the flux density. Flux density can be defined as, if you consider an area, A here, you consider a area A, number of flux lines passing through this area, can be considered as magnetic flux density B. Magnetic flux density B. Therefore, if you want to know how much flux is passing through this area, if you want to calculate the flux, you can calculate it by phi is equal to B into A. Flux lines can be calculated by phi is equal to B into A. So by writing it, phi is equal to mu naught mu r Nia divided by 2 pi r. As we know that, as we have described it, n is number of turns, I is current through the copper wire or copper conductor. A is area of cross section. And R is the radius of the toroid. This phi can be further simplified by considering this 2 pi r, by considering this 2 pi r as L, where L is equal to 2 pi r, which is length of the mean flux. L is 2 pi r, which is length of the mean flux. So this phi can be written as mu naught mu r into n into I divided by L, where L is the length of the mean flux. So this can be further written as n into I divided by L divided by mu naught mu r into A. So this we can reduce as this term L divided by mu naught mu r into A. This we can reduce as reluctance. Okay, reluctance of the magnetic path. Reluctance is similar to the resistance in an electrical circuit. In a magnetic circuit, reluctance is similar to resistance. So as you can see here, this phi is equal to mmf divided by reluctance, where phi is similar to that of the current, where mmf is similar to that of the emf in an electrical circuit, and r reluctance is similar to that of the resistance in an electrical circuit. So this reluctance R can be expressed as L divided by mu naught into A, where you know that mu naught is the permeability of the free space. Mu naught is the permeability ability of the free space. Mu naught is the permeability of the free space. Mu r is the relative permeability. Mu r is the relative permeability, and A is area of cross section. The SI unit of mu naught is ampere turns per Weber. SI unit of mu naught is ampere turns, that is Ni divided by Weber is flux. So we know that as I have written here, phi is equal to mmf divided by r. Therefore, reluctance R is equal to reluctance R is equal to mmf divided by phi. The SI unit of mmf is ampere turns, and SI unit of phi is Weber. So the SI unit of reluctance is ampere turn for Weber. Okay, just delete it to make some space. Ampere turns for Weber. So the inverse of the reluctance is permeance, but permeance is the permeance is similar to the conductance. Permeance is similar to that of the conductance in an electrical circuit. Permeance is similar to that of the conductance in an electrical circuit. Permeance similar to the conductance in an electrical circuit. Which is represented by rho, which is equal to 1 by r. So this is again as flux is equal to mmf by reluctance. Similar, as I have told this before, is similar to that of the electric current, which is equal to voltage by resistance, or emf by resistance. So let us see this. This one we'll look into it later. So let us see this analysis of a simple magnetic circuit. A simple magnetic circuit can be analyzed as before, as like this. So we have this n is the number of turns, I is the current through the conductor. Therefore, Ni can be considered as the voltage, or this can be written as F. This can be written as F. So the flux flows as the flux lines, as you can see, is the length of the mean flux. L is the length of the mean flux. So this flux can be represented in terms of current I. This flux can be represented in terms of current I in an electrical circuit. This F can be represented in terms of voltage in a magnetic circuit. And we have a reluctance similar to that of the resistance. We have reluctance which is similar to that of the resistance in a electrical circuit. This H is magnetic field intensity. Magnetic field intensity into the length of the mean length of the flux will give you the reluctance of the circuit. So here we have a comparison between electrical circuit and magnetic circuit. So we have EMF E, which is similar to that of the Ni. MMF current is similar to that of the flux. Resistance is similar to that of the reluctance, and we have the equation current is equal to voltage by resistance is similar to that of the mmf divided by reluctance in a magnetic circuit. So let us look into a problem. First, you have to consider a magnetic circuit as shown in the figure. You have to consider a magnetic circuit as shown in the figure. So what is the rectangle area? It has a rectangle area of 8 centimeter width. That means the width is 8 centimeter. This width is 8 centimeters. This width is 8 centimeter, and sorry. width is 8 centimeters. Width is 8 centimeters. This height is 20 centimeters. This height is 20 centimeters of the core. Okay, there is an air gap of 2 millimeter. This air gap, there is an air gap of 2 millimeter air gap. Okay, cross sectional area. Cross sectional area means this one. This cross sectional area. This is 4 into 4 centimeter. That is 16 centimeter square. 16 centimeter square is the cross sectional area. Number of turns N is equal to 400, and relative permeability of the iron is 4000. So you have to find the current I, which is required to establish a flux density of 1.2 Tesla. You need to find out the how much current is required to be fed through the copper conductor in order to establish a flux density of 1.2 Tesla. 1.2 Tesla. So this circuit can be represented in terms of an electrical circuit. As you can see here, this is F is equal to Ni. You know that F is equal to Ni. This is flux. These are the reluctance. One is reluctance of the core, and another one is reluctance of the air gap. So we have to add it in order to get the overall reluctance. R is equal to reluctance of the core plus reluctance of the air gap. So from this we can obtain the flux, and from the flux we can obtain current. From the flux we can obtain current. So first let us calculate the magnetic line path. What is the length of the magnetic path? We have to calculate the length of the magnetic path. That is the whole circumference or whole length of this path. Okay, that is, we know that the height is 20 centimeter. 20 centimeter height plus 20 centimeter plus 8 width minus the air gap, which is 0.2. So total magnetic length is 55.8 centimeter. So we know that area of cross section is given. Area of cross section is 16 centimeters square. Okay, area of cross section is 16 centimeters square. From this we can calculate the reluctance of the core. From this we can calculate the reluctance of the core. The reluctance of the core is equal to LC, the length of the core, length of the magnetic line path in the core, LC, which is 55.8 centimeter 10 to the power of minus 2, divided by mu naught is 4.4 into, how much is mu naught? 4, you know that 4 pi into 10 to the power of minus 7. Mu naught is 4 pi into 10 to the power of minus 7. 4 pi into 10 to the power of minus 7. We have mu r, which is 4000. Mu r is 4000 into area of cross section, which is 16 centimeters square into 10 to the power of minus 4, because it's centimeters square. Okay. So the resultant will be 0.69832 into 10 to the power of 5 Henry. Okay, the reluctance of the core is 0.69832 into 10 to the power of 5 Henry. Similarly, we can calculate the reluctance of the air gap. Reluctance of the air gap. In order to do that, we need length of the air gap. We know that length of the air gap is 0.2 centimeters. So we'll put length of the air gap divided by mu naught, because air gap is the mu naught. There is no relative permeability because it's in the air, and area of cross section of the air gap, which is also equal to as area of cross section of the iron, and area of the cross section of the air gap is 4 into 4 centimeters square, which is also is equal to 16 centimeters square. By substituting the length of the air gap for mu naught, which is 4.2 into the power of minus 7, and air gap, which is 16 centimeters square, we will get 9.9472 into 10 to the power of 5 Henry. So the overall reluctance will be 0.69832 into 10 to the power of 5 plus 9.9472 into 10 to the power of 5 Henry. As you can observe here, the reluctance of the air gap is much higher than the reluctance of the core. That means it is much difficult for flux through pass through the air gap than compared to that of the magnetic core. That is why in the beginning we considered that there will be negligible flux in the air. The leakage flux in the air will be negligible because the flux lines in the magnetic core will be very much higher than that of the flux lines. Number of lines of magnetic flux in the air. So the overall reluctance, we can calculate it as R is equal to RC plus RG. R is equal to RC plus RG. So we know that I is equal to or uh, or we know that R is equal to MMF divided by R is equal to MMF divided by reluctance. R is equal to MMF. Sorry, I is equal to MMF divided by reluctance. MMF is equal to flux is equal to MMF divided by reluctance. We know that flux is equal to MMF divided by reluctance. I will write it again. We know that flux phi is equal to MMF divided by reluctance. Okay, and phi is equal to MMF is N into I divided by reluctance. Therefore, I is equal to flux into reluctance divided by number of turns. Flux into reluctance divided by number of turns. We don't have flux, but we do have flux density B. And we know that flux is equal to flux density into area of cross section. If phi is equal to B into A. By substituting it in the equation, I is equal to B into A into reluctance divided by number of turns. B into A into reluctance divided by number of turns. So we can substitute it here. We know that B is given as 1.2 Tesla and area of cross section is 16 into 10 to the power of minus 4 as it is 16 centimeters square. Then we have reluctance as 10.641 into 10 to the power of 5 divided by number of turns is 400. So the current required to establish a flux of 1.2 Tesla is 5.108 ampere. 5.108 ampere. So